Dear students, welcome to the operating system video lecture sessions. In order to continuation to the previous video, in this video, we are going to discuss about round-robin CPU scheduling algorithm. So here we are going to discuss, we have already discussed basic concepts and scheduling criteria. Now we are discussing the last scheduling algorithm, round-robin scheduling algorithm. Previously we have discussed first come first serve scheduling algorithm, shortest job first scheduling algorithm, and priority scheduling algorithm. We have already discussed. You can check those videos. The objectives of this lecture videos is to introduce the CPU scheduling and to describe various scheduling algorithms and evaluation criteria for selecting the different CPU scheduling algorithm for the different scenarios. So outcome of this lecture video is you can be able to apply round-robin scheduling algorithm onto the different processes to calculate the average waiting time for the given process. Round-robin scheduling algorithm. So each process gets a small unit of CPU time. Generally, it is 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. The meaning of this one is each process is associated with some quantum time. That is, some timeline will be associated with each and every process. Say it might be 10 to 100 milliseconds, or that is custom. A different time limit may be given. So whenever, for example, there is a 10 processes, P1, P2, P3, and there are 10 processes, right? If there are 10 processes, P1, P2, P3, and so on, so each and every process is associated with some time limit. So 5, if I say generalized 5 time, so even it is burst time is 20, the CPU will be allocated for this process one is only 5 units of time. Then immediately that will be sent to the queue and P2 will be given with CPU for the 5 units of time and so on. So this will be happened. If there are n processes in the ready queue and the time quantum is q, that is the time quantum we will assign, then each process gets 1 by n of CPU time in chunks of most q times, that is time quantum times units at once. So no process is going to wait for the CPU. Right. So timer interrupts every quantum should schedule next process. When the one process is completed, the next process will come. So the performance generally, quantum time is large for the first in, first out. But quantum time is small for this round robin, and Q must be large with the respect to the context switching. Otherwise, overhead is too high. So this context switching we have already studied. Context switching is changing from one process to another process. If the time quantum is high, then only it will be good. The number of context switches will be less. If the time quantum is very less, then number of context switches will be high. We have already studied that context switch must be less. Then only your processes will complete fast. So now we will check one example with time quantum 4 and we will apply round robin scheduling algorithm. So as we have discussed, round robin scheduling algorithm will follow some time quantum. So for this problem, there are 3 processes has given. The burst time is 2433 respectively, and the quantum time is 4 units of time. Now let us draw the Gantt chart and we will try to find out the average waiting time and we will check it. So there are three different processes, process and burst time, process P1, P2, P3, three process there. First process is 24 units of time, second one is 3, third one is 3. And the given time quantum is 4 units of time. Now draw the Gantt chart for this. The Gantt chart will start from 0 and the first process is P1, but time quantum is 4, so it will stop and take another process into consideration after 4 units of time. Then P2 is having 3 units of time, so 4 plus 3 is 7. Then P3 is 7 plus 3, 10. After completion of P3, again your scheduler will go to P1. So P1 is completed only 4 units of time here. So still there are 20 units of time. So P1 will come again, it is 14. P2 is completed and P3 is completed. So again, P1 will take that CPU, that is 18. Again, P1 will take 22. Again, P1 will take 26 units of 4 units of time. Then again, P1 is 30 units of time. See, just count here. 4 units of time here. Then 4 plus 4, 8. 12, 16, 20, 24. So with this, it has completed 24 units of time. Now calculate the waiting time for each and every process. Waiting time for P1. What is P1 waiting time? Here it is 0. P1 waiting time is 0. Coming to here, again P1 is there. P1 waiting time is 10, but it is already utilized CPU here for the 4 units of time. So 10 minus 4, it is 6. For the PTU waiting time, P2 waiting time is 4 units of time. For the P3, the waiting time is 7 units of time. Now calculate average waiting time. That is 6 plus 4 plus 7 by 3. It is almost 17.3 means 5.66 milliseconds are unit time. 5.66 time units it will consider by using round robin scheduling algorithm. So in this way, you are going to apply round robin scheduling algorithm onto the given processor and given time quantum. So this is about your Gantt chart. So with this Gantt chart, you can calculate the average waiting time. So higher turnaround time than SAF. So generally round robin will have higher turnaround time. But it will be having better response that because the context switching immediately it is having time quantum, so context switching will be happening. So Q should be larger, that is time quantum should be large compared to the context switch time. So context switch time, it is not good to change the process every time very frequently. So that is the caution we have to take. Generally, time quantum must be 10 to 100 microseconds, then it will be more optimized. So if you take this if you see this time quantum and context switching, if you are taking process time is 10 units of time, then at a time, if the quantum is process time is 10, if you are taking the time quantum t is equals to 12, then you need not to switch anything. Directly the process will be completed. So the number of switches will be 0. If the process time is 10, that is the burst time is 10, and the quantum time, the t value, if you are taking 6. So after 6 units of time, it must have to change to other process. Again, it have to come to its own process. If there are no processes also, again it have to process 1, stop processing, and again it comes to the same process and it will complete. So again, in this case, it will context switches will be 1. If you are taking the process time is 10 and quantum is 1, the quantum timeline is 1, then you have to, for every 1 unit of time, it must have to do context switching. So the total number of context switching is 9. So with this, what we have to understand is quantum time must be high. Then only the context switching will be less, than your CPU will be optimized. So this is all about round robin scheduling algorithm. In the next class, we will discuss the further concepts. Thank you. Have a nice day.